Every summer, we rely on refrigeration to keep us cool, and almost all of it depends on compressing and expanding some kind of working fluid. But what if we could do the same thing without any fluids at all? There's a really interesting effect that occurs in ferromagnetic materials. When you place them in an external magnetic field, their temperatures actually increase. And when you remove them from the field, the temperatures drop. This phenomenon is called the magnetocaloric effect, and it has the potential to completely change how we design refrigeration systems. So what's actually causing this temperature change? And how can we implement it in a cycle? Let's zoom in to the atomic scale. In a ferromagnetic material, each atom acts as a tiny magnetic dipole. Without an external magnetic field, these dipoles are randomly oriented, placing the material in a high magnetic entropy state. From the second law of thermodynamics, the total entropy of the magnetocaloric system can be expressed as the sum of the thermal and magnetic contributions. This means that entropy changes can come from both temperature and applied magnetic fields. Unlike vapor compression cycles where entropy changes are driven by fluid phase change, here entropy is directly controlled through magnetic fields. If we take a look at the temperature versus entropy diagram, we can plot out each point as we go throughout the cycle. Now if we apply an external magnetic field, the dipoles begin to align with the field. This reduces magnetic entropy of the system. If heat were allowed to leave the system, the process would be isothermal, but if the system were designed to be adiabatic, something entirely different happens. Because heat can't escape, the decrease in the magnetic entropy is going to be balanced by the increase in the lattice entropy. This shows up as a rise in temperature. Now the material is hotter, but at the same initial total entropy state. If we keep the magnetic field applied and allow heat to leave the system via some secondary loop, we see that there's a temperature drop along with the decrease in total entropy. Now we remove the magnetic field in an adiabatic process. As the field is reduced, the magnetic dipoles begin to randomize, increasing magnetic entropy of the system. Because no heat is exchanged, this increase is balanced by a decrease in lattice entropy, which results in a drop in the temperature. Now that the material is colder than the object we want to cool, we can then bring them into contact. Heat flows into the material, increasing its temperature and entropy, while cooling the object. By cycling through these 4 steps, we can continuously pump heat, just like a traditional refrigerator, but without the need of refrigerant gases. For the cycle to be effective, the material needs to respond strongly to a magnetic field, but that only happens below a certain temperature. This is called the Curie point. Above it, a ferromagnetic material loses its magnetic ordering and becomes much less responsive to an external magnetic field. To demonstrate this, I attached a steel bolt to a magnet and heated it up in the oven. As the temperature increases, the magnetic forces weaken, until eventually, it can no longer support the weight and the bolt falls. For magnetocaloric refrigeration, this is critical, since the strongest alignment with the field occurs when the material operates near its Curie temperature. So choosing the right material means selecting one with the Curie point close to the desired operating temperature. This is why gadolinium is typically used to create magnetocaloric refrigeration cycles. Its Curie point is around 20 degrees Celsius. Another widely used material is lanthanum iron silica. This material has a tunable Curie temperature, making it viable for commercial solutions. While there are still challenges in materials and system design, this technology has the potential to achieve high efficiencies and reduce environmental impact. As research continues, magnetocaloric systems could be a viable alternative to conventional refrigeration. Thanks for watching.